Hey guys, uh, so my name's Christopher Chu, and basically what I want to show you is, hold on. I want to I want to show you a presentation of research of human and robots. The paper is called Advancing Humanoid Locomotion, Mastering Challenging Terrains with Denoising World Model Learning, and it's a collaboration between researchers from the Royal Era, the Tsinghua University, and Shanghai Chizhi Institute. The goal here is I want to address challenges of humanoid locomotion. I want to introduce learning-based approaches along with humanoids to walk on challenging terrains, which include slopes, stairs, and deformable surfaces. I also want to describe the humanoid locomotion that was presented in the paper, which is complex control, disturbance, and sensor noise. I'll go over why it's so difficult to find existing solutions, and then the proposed DWL framework. And then finally, I'm going to finish with reviews on the real-world performance of the DWL algorithm. So why is humanoid locomotion such a hard problem? Well, unlike wheeled robots, humans must maintain balance while walking on diverse terrains. This is hard due to three challenges. Number one is the high center of gravity. Humanoid robots are less stable than quadrupeds, which means that the center of mass is higher than the ground, making them prone to tipping over and encountering uneven surfaces. Human robots also have greater log inertia. The humanoid robots have long legs of humanoid high inertia. It's hard to control, and any slight miscalculation will result in falling or very inefficient walking patterns. Finally, the dynamic balance equipment. Humanoids must constantly adjust posture while walking, and we need to predict and compensate forces in real time. And the approaches that was used in Gazebo and other robotics ID softwares unfortunately fail to generalize in real time. So basically what I'm saying here is we need to find a new strategy to be able to resolve these issues. Now, the existing solutions, several control methods are explored for humanoid locomotion, but each comes with limitations. Number one are traditional control methods. The most common is zero movement and model predictive control. They rely on accurate environmental models. There's less effective unpredictable terrain such as sand and ice. Number two is reinforcement learning approaches, which allows robots to learn from experience, which makes it more adaptable. And however, it has simulation to real model transfer issues. Model runs simulations fails in the real world due to physics, and then also sensor noise and friction, as you can see from the robot on the right. We need a way to use reinforcement learning to make it robust to uncertainties, which is why we proposed, or the scientists proposed, a method called Denoising World Model Learning, which is a novel-based reinforcement learning framework handling real-world challenges. So here we see an encoder-decoder framework. The Denoising World Model Learning reconstructs noisy and missing sensor data, which results in more accurate decision making. It also spreads the simulation to real-life gap. Unlike reinforcement learning, Denoising World Model Learning learns robust representation of the environment without retraining the real world. There's also zero-shot transfer, which the Denoising World Model Learning doesn't require real-world tuning to make deployment faster. There's also robust sensor noise. Denoising World Learning functions with missing and corrupted sensor data, which is very good. And we were able to handle real-world dynamics, adapt to changing terrain conditions, and improve locomotion in unpredictable environments. So, the breakdown of the technical aspects of Denoising World Model Learning. As for the encoder-decoder network, the Denoising World Model Learning uses the encoder to compress and sensor observations, which will help to filter out noise. The decoder is also reconstructing the clean system state. The robot will make better locomotion decisions. We also have proximal learning with proximal policy learning, which The robot will use the proximal policy learning, aka Q learning, to learn optimal learning strategy based on clean data. It prevents overfitting the simulation, which makes the model more adaptive. There's also an active 2 degrees of freedom, where in a traditional humanoid, you can see it has passive ankle joints, and denoising world model learning has 2 degrees of freedom of ankle control. It allows the bot to dynamically adjust foot placement for better balance in uneven surfaces. So you can see the diagrams here, denoising world model learning, and you can see the sensor pipeline and the effect on ankle stability. In this particular diagram, we use IMU data, we encode the data to a latent state representation, and then we reconstruct the missing state using a decoder and clean sensor data, and then we use proximal policy optimization to be able to generate motor control commands, which helps the robot to adapt to certain ground conditions. So for the experimental setup results, validating the denoising world model learning, the scientists conducted real-world experiments on various terrains and slopes and stairs. The denoising world model learning allowed the robot to walk smoothly on the rails and the steps. In the deformable ground, such as snow, which is moldable, the denoising world model learning navigates soft and unstable terrain. Also, in the external disturbances, the robot can recover from unexpected forces such as being pushed. It's able to get back up without falling. The denoising world model learning fortunately achieved 100% success in real-world trials, and it outperforms traditional reinforcement learning and passive income control methods. And you could see the denoising world model learning velocity curve on the right of the slide, and it will also result in, it will auto-adjust and result in smoother movement and better stability. Kind of like a very effective version of PID control. So in conclusion here, we could see that the denoising world model learning basically worked like a charm and was able to make the robot be able to control itself properly and be able to adjust itself in real world, and we were able to transfer it from simulation to real world, and it outperforms existing methods. Furthermore, what the research can take is cameras can be put on the robot. Since this robot only got sensor data, we could have cameras on the robot with a trade-off for more data to be able to garner more training data for the robot, and later the robot can be trained for higher speed locomotion once the test experiments are done. And that's basically it. Thank you guys for listening to the presentation, and see you soon. Peace.